Hi, class. Welcome to chapter 13. This is the last chapter in Calculus 2. Today we are going to talk about sequences. This is chapter 13.1. If at any point or even beforehand that you feel you are having some problems with this section, you can look at my pre-calculus material. I have a section on sequences there. We do not go as in depth in the pre-calculus stuff, obviously, as we do for this Calculus 2 material. So it might be a nice sort of way to get your toes wet, so to speak. So if you're having problems in this section, you can go and you can look at the pre-cal stuff, or you can preface this section by looking at the pre-cal stuff first. Okay. So for chapter 13, this is really the only section where we're talking about sequences. The remainder of the sections in chapter 13 are about series, which I also have pre-calculus stuff to help you get your feet wet with as well. So let's go ahead and talk about sequences. So a sequence is a list of numbers that follow a pattern. Okay. The pattern is called A sub n. This is the term you're going to see everywhere. A sub n is generally given by a rule. Okay, so one way to notate a sequence is to have your sequence between curly brackets. Another way is to have these curly brackets, but then to specify the starting place and the ending place for our sequence. And then we can write it as a list as well. Okay, so you guys are already familiar with this because we've gone over series quite a bit, right? We started this course off with review of left and right hand sums, the Riemann sums. And so it's very, very similar to that. We're just not adding everything together, right? So later on in this chapter, that's what we deal with when we have to add everything together. And that's what we're going to be studying. But for right now, we're just looking at the terms themselves and what they're doing, okay? So note that our sequence starts at n equals 1. So let's do a couple of examples. Let's say that my sequence is given by n divided by 1 plus n squared. So obviously the first entry into my sequence is I'm letting n equal 1. Okay, so if n is 1, I get 1 over 1 plus 1 squared, which is going to give me 1/2. The next term is the second term, so n equals 2. So I have 2 over 5 because I have 1 plus 4, right? 1 plus 2 squared. So I have 2/5. The next one is the same thing. I'll have 3 over 1 plus 9. So I have 3 over 10. And you can see the pattern, right? So I'm squaring the bottom number for its term of n, and I'm adding 1 to it, right? My numerator is just counting by 1. 1, 2, 3, 4, 5, 6, etc., etc. The bottom number is that top number squared, and then 1 added to it, right? So 2 squared plus 1, 3 squared plus 1 is 10, 4 squared plus 1 is 17. The next one would be 5 over 26, and so forth, right? So generally what we do is if we don't already know what the formula or the rule is for the sequence, we generally will write it in the sequence itself after these dot dot dots, right? And then we will continue to write dot dot dots afterwards. So it's kind of like, the empty space. Okay. So let's look at another example. So for these following examples, we want to list the first four terms. So for A, uh, our sequence A sub n is given by -1 to the nth power times n over n factorial plus 1. Okay, so what's going to happen here is that I have -1 to the nth power, which means that when I start at 1, I get -1 to the first power, just -1. For the second one, it's -1 squared, so it's a positive. The next term is -1 cubed, so it's negative. So it's going to alternate in sign from negative, positive, negative, positive, negative, positive. Okay. The numerator is just n. It's just going to go up by 1, just like the previous one did, alternating in signs because of this -1 term. And then if you don't know what factorial is, if we haven't talked about it yet, and if you haven't seen it in any of your studies, factorial means that you are multiplying numbers that go down in value by 1. So 5 factorial, for instance, would be 5 times 4 times 3 times 2 times 1. Okay, we stop at 1. We do not include 0 because if we included 0, it would always just be 0, right? So 10 factorial would be 10 times 9 times 8 times 7 times 6 times 5 times so forth and so forth and so forth. Okay. The only other thing that I should probably point out is that 0 factorial is equal to 1. So we do have 0 factorials, but it is not 0 times anything. It is just the value 1. Okay. So if we look at this, my first term, -1 to the first power, will be negative. I have a 1 in the numerator, and then 1 plus 1. So I should have a -1/2. Okay. My next term should be a 2 on top, and it should be positive because it's alternating. On the bottom, I should have 2 times 1 plus 1. So that's just 2 plus 1. So I have 2 over 3. My next one will have a 3 on top. It'll be negative. And on the bottom, I'll have 3 times 2 times 1 plus 1. So that's 6 plus 1. So 7. So 3 over 7. Right? And then the next one, I will have a 4 on top. It'll be positive, and it'll be 4 factorial plus 1. So 4 times 6 is 24, plus 1 more is 25. Okay. So that's my first 4 terms. So for B, we have a slightly different form. It's saying that A1, the first term, is equal to 2. And then my next term, n plus 1, is equal to my previous term divided by 1 plus that previous term. So in order to kick this off, n is still 1. So A is subscript here 1 plus 1. So A2, the second term, is going to be A1 divided by 1 plus A1. Well, what is A1? It's 2. So my second term is going to be 2 over 1 plus 2. So 2 over 3. So my first term is given to me. That's nice. The second one, I actually had to calculate by using the first term that's given to me. So that's 2 over 3. And for my next term, I'm taking 2/3, the previous term, and I'm putting it in the numerator. And on the bottom, I'm going 1 plus this value, right? So 1 plus 2/3 is 5/3. Okay, so I have 5/3 in the denominator, 2/3 in the numerator. Remember, when you multiply fractions, you multiply and flip. So this should actually be 2 over 5. Okay, and then if I do the same thing here, 2/5 in the numerator, 5 over 5, so that's 7 plus 5 on the bottom. So when I multiply that out or divide it, it's 2 over 7. And there we go. So I'm pretty sure the next term would then be 2 over 9, 2 over 11, 2 over 13, etc., etc. So I could rewrite this more like this top term, right? This initial way that I showed you guys, but we can also write it what is called recursively, right? So this bottom term is a recursive form because I'm given the first term and all the next terms are dependent on what the previous term was. So it's called a recursive form because I'm always taking my previous answer and plugging it in to find the next answer. Okay, so it's a recursive sort of thing that we're doing. Next example is find a formula for the general term a sub n of the given sequence. So this is something that's much, much more common. Um, yeah, we will have to uh, find the terms. That's something that we are definitely going to be doing, right? So you'll be given a formula like this, and then yeah, you got to find a few of the terms. But it's also very common to be given a sequence, and then you have to find the general form for it. This is a very, very common thing, and it can be very, very difficult to do. Okay, so we'll talk about some common things that we see and some common ways to um, put the general term together for a sequence. So here we have 4, -1, 1/4, -1/16, 1/64. So there's a few things that are going on here, right? So we really want to analyze what the pattern is. So the first thing that I notice is that I'm alternating in signs. Positive, negative, positive, negative, positive. The next one should be negative, right? And it'll continue to alternate forever. Now, in our previous example, when I had -1 to the n, I started off with a negative. Here, I'm starting off with a positive. So remember, whenever my power is odd, like 1, starting off at 1, I get a negative when I have -1. So I need to have some sort of an even power. So I can go n minus 1, or I can go n plus 1, or there's other ways I can creatively do that, but typically we try to keep it simple. So since I'm starting at a positive and I'm alternating in sign, I should have a negative 1. Okay, let's come up here real quick. I should have a negative 1 to the n plus 1 power in order to alternate signs like I did before, but start off at a positive. Oops, too far there. Okay. The other thing you might notice is that I am basically dividing by 4 each time, right? So if I start off with 4, if I divide that by 4, I get a 1. If I divide 1 by 4, I get 1/4. If I divide that by 4, I get 1/16. If I divide that by 4, I get 1/64. Another way to think about that is I have powers of 4 in the denominator, right? So the powers in the denominator are increasing is another way. So taking all those things that we've kind of noticed from our sequence, we'll look at them one at a time to try to build our model, right? So the first thing is we can see that everything is dividing by a factor of 4 in order to find each new term. Not only is it dividing by 4, but it also starts at 4. So whatever it is that I put down on paper, when I plug in 1 for n, it needs to give me a value of 4. That's positive. And when I start to increase by 1 for that, wherever I put the n, it needs to increase the power in the denominator by 1 for a 4. Okay. So using n plus 1 will help me start at a positive and alternate signs. I know the denominator is increasing by a factor of 4 every time, or power of 4, I should say, not a factor of 4. I guess it's actually the same thing. So I need n equals 1 to give me 4 for the first term, right? And then I need it to reduce by a power of 1 for each new term so that I can be dividing, right? So I need a formula that as n increases by 1, the power attached to this 4 is going to decrease by 1 each time because I'm dividing here, right? So I'm going to use negative 1 to the n plus 1 for this alternating terms, positive, negative, and then I'm going to have 4 to the 2 minus n as my power. So notice that when I plug in 1 for n, I get 2 minus 1, which is 1. So I have 4 to the power of 1, which is just 4. The next value of 2, 2 minus 2 is 0. 4 to the 0 is just 1. And then this turns negative. When I plug in 3, I get 2 to the negative 3, or 2 minus 3, I'm sorry, which is the negative 1 power, or 1/4. And so this checks out, right? Make sure you check your formula with your terms to make sure everything works. I can write this a different way, okay? If I want to write it in terms of thinking of dividing by 4 instead of powers of 4, I can write it as 4 to the n minus 2 power. So that when I plug in 1, I have a negative power, which makes this 4 go to the numerator position. When I plug in 2, it's just 0, so that's the 1. And then when it's 3, it's a positive power on the bottom, so that's 1/4, and so forth and so forth. Here, remember, I just need this power to start at an even number for this negative 1, so it starts off positive. So if I plugged in 1, well, 1 minus 1 is 0. Anything to the 0 power is just 1, so that's a positive multiple of 1 here. Okay, so both of these are equivalent ways of writing this formula. Now, if you look really closely, this n minus 2 term, if I were to write it in line, uh, it would actually equal 2 minus n, right? So if I wrote 4 to the negative parentheses n minus 2 power, okay, so that I could write it like this, and I distribute that negative sign, it would actually go to 4 to the 2 minus n power. So these two things are actually equivalent, which makes sense because it is the same sequence. But you can write them different ways. You can start your n at crazy places if it works out, if you are, you know, multiplying things in the same way, but it's much, much easier to think, just kind of try to keep things as simple as possible. Okay. So now let's look at our next sequence, B. Here, if we kind of look and see what's happening, I notice right away again that I'm alternating in signs, starting at a positive. So I need to have this negative 1 to the n plus 1 power so I can start positive and then alternate. Or I need this negative 1 to the n minus 1 so I start positive and then alternate. Typically, you'll see the plus form. Not any reason at all, it's just a preference. Okay. Um, I notice that my denominator is increasing by 1 each time. 2, 3, 4, 5, 6. So it's very clear that there's an n in there because as I'm going, I'm increasing. However, I'm not starting at 1 in the denominator. I'm starting at one more than that, which is 2. So in the denominator, I probably have an n plus 1. So that when n is 1, I end up with 2, right? When n is 2, I'm adding 1 to it, so I have 3 in the second term, 4 in the third term, 5 in the fourth term, right? It's off by 1, so the denominator is n. It's still counting up by 1, uh, but it's shifted as well. If you look at the numerator, these are all powers, right? This is 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. So the numerator is just n squared. Whatever term I'm on, I'm squaring that numerator. So I have my alternating signs. The numerators are all squares, where their square roots are the things that are increasing by 1, right? 1 squared, 2 squared, 3 squared, 4 squared. And the denominator increases by 1 every time, but it starts at 2, so it's been shifted by 1. So that sequence would be -1 to the n plus 1 power, n squared on top, n plus 1 on the denominator. So let's go ahead and look at a few definitions. So a sequence, a sub n, has a limit, which we call L, and we write that the limit of the sequence as n goes to infinity is equal to that value L, right? Or another way to say that is that as my sequence approaches L, my sequence approaches L as my n values get very, very large. So I look at when I'm looking really, really far down the terms of in my sequence, the values in my sequence, those terms I'm looking at, get very, 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 very close to this value L if the limit exists. Okay, so so this limit exists if we can write the terms for an as close to L as we like by making sure that n is large enough, very large value. Okay? So if the limit exists, we say that the sequence converges, okay, or is a convergent sequence. Otherwise, it diverges, or what we call a divergent sequence. Okay. So next definition, a sequence, a sub n, has the limit L, and we write again that the limit as n goes to infinity of our sequence equals L, or my sequence goes to L as n gets very, very large. If for every epsilon larger than 0, so basically for any value, small value that I look at that's larger than 0, there's somewhere where past that point, the distance between the term in my sequence and that limit is less than my choice of epsilon. Okay. So again, this is really a more formal way of saying what we have up top, right? The top definition is really talking about convergent and divergent. The bottom definition is really talking about the definition of the limit, right? So what this is saying, again, let's reiterate this, okay? When I look at very, 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 very large values, right? If I say I want to be within a tolerance of the limit, somewhere after some point, all my values should be within that tolerance, okay? The distance between my terms and the limit of the sequence will be less than my tolerance that I choose. Right? So if I'm saying, hey, I need all of my terms in my sequence to be 0.00001 away from where I think it converges to. Okay. Then at some point, every single term past that point, okay, so once I get to some point, every term past that point, the distance is within the tolerance, that 0.00001 that I need to have. Okay, that's basically what the limit is saying. So at some point, I am within a tolerance, no matter how small the tolerance I decide to choose. Okay, so graphically, let's kind of look at this. The first few terms just kind of do whatever. You can see we're kind of like we're bouncing around, but we're kind of like getting tighter and tighter and tighter. Let's say that my limit is somewhere in between these first few terms of the sequence. Okay, this little squiggly means I've gone quite a few, so this n can be at 100, it could be at 50, it could be at 1,000. It really just depends on what my sequence looks like. So after some point, however, I tell myself I want to be really, really, really close to this limit. How close do I need to be? Well, I need to be within epsilon. So on the graph, that's my limit plus a little bit more, plus epsilon more. And so once I hit this point, I'm now within that tolerance. Okay. And that is above and below, right? We call this an epsilon ribbon because in the middle is the middle of my ribbon, and then I have my edges that are equidistant, right? And so once I hit that big N for any term of my sequence past that point, I am always within epsilon of my limit, and I should be approaching my limit more and more and more as I get farther and farther um, down the terms of the sequence. Okay, so theorem: if the limit of f of x, I have a function of x, as x goes to infinity, is equal to the limit L, and f of n equals a sub n. So what this means is whenever I am at n, so let's say f of 1, I will be equal in value to the first term of my sequence. At 10, my function will be equal to the 10th term of my sequence. At 1,000, my function will have an output that's equal to the 1,000th term of my sequence. Okay, so basically my function hit certain points, at certain points, whenever I hit an integer, it's equal in value to my sequence. Okay, where n is an integer, obviously. Then the limit of my sequence, as n gets very large, also goes to that limit L. So that is a very powerful theorem, right? We don't really use this yet. We use this like towards the end in chapter 13.9, 10, 8-ish a little bit. So we use this quite a bit later, but this is an important theorem right here. Okay. So, if the limit of my sequence as n goes to infinity is infinity, it just keeps getting larger and larger and larger, then that means that for any choice I choose of m, where m is just some positive number, okay, there is always going to be some integer n along the number line where whenever I look at values larger than that value, okay, so if I look at terms of my sequence larger than that value, then this value of my sequence is larger than that value of m that I chose. So basically what this means is that if my limit goes to infinity, the terms just get bigger and bigger and bigger. It doesn't matter where I try to cap my sequence at, I can always find a value larger. Right? So let's say that my sequence grows in value really, really slowly. Um, if I say, hey, I think that my sequence will never be larger than 1,000. If it does not converge to L, if it what we call diverges, right, meaning it just gets bigger and bigger and bigger, somewhere once I hit a certain point, all the terms after that term will be larger than that cap of 1,000 that I tried to set. Okay. So now let's look at limit laws for sequences, right? So basically what this means, this previous definition means I cannot bound my sequence above if it is divergent, if it goes to infinity. The limit goes to infinity. Okay. Limit laws for sequences. If A is the sequence and B is the sequence, and they both converge, meaning that as we look at really large values, it gets really, really, really close to some value. Okay. And let's say that C is a constant, then the limit as n goes to infinity of an plus bn or a minus b is going to be the same as the difference or the sum of their limits. Okay, so whatever the limit is here, where I'm adding all the terms of the sequence together and then taking their limit, it would have been the same as if I split the terms, I'm sorry, split the sequences apart and just took their individual limits and added them or subtracted them. The limit as uh, c times the sequence as n goes to infinity is the same thing as just that constant times the limit of the sequence. Okay, so these are really just the same laws that we had from limits from way back in Calculus 1. That if you need to look at that again, you can review that as well if needed. Okay. The limit as n goes to infinity of a constant sequence is just that constant. So for instance, this would be like if my sequence was 1, 1, 1, 1, 1, 1, 1, 1, right? If it was nothing but ones, well, it's not diverging from that at all. It's not going above or below. It's always just one. Then that means that that's the limit, right? It doesn't differ from that at all. Okay. The limit as n goes to infinity of the product of my sequence, right? Or the product of the terms of my sequences. So first term of A times first term of B, and then the second term of this would be the second term of A times the second term of B, and so forth, so forth. This would be the same as if I just took the limit of the individual sequences and then multiplied them together. Obviously, from this comes this ratio property, right? The limit of the ratios of each term in the sequence is the same as if I just took the limit of one and divided it by the limit of the other, as long as the limit of Bn as n goes to infinity is non-zero, because we cannot divide by zero, right? The limit of a sequence as n goes to infinity, if that's every term in that sequence is raised to the power of p, it would be the same thing if I just raised the entire limit to the power of p. Okay? As long as p is positive and every element in the sequence, every term in the sequence is also positive. Right? So let's talk now about the squeeze theorem. The squeeze theorem is a very, 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 very important theorem. We saw this in when we're talking about integrals. I think we talked about this with derivatives as well, right? The squeeze theorem is kind of everywhere. So basically, what is happening is that we're going to have some function that is larger than, sorry, not function, some sequence that is larger for every term than another sequence, but it is also smaller than another sequence, right? So the one that we're focusing on right now is this B. So every uh, term in B is larger than its equivalent term in A and its equivalent term in C. Okay. For all n's from the beginning and on, right? So n0 and not, basically, it's the first n and forward, okay? And that the limit of the sequence A as n goes to infinity is going to be equal to the limit of C as n goes to infinity. So all the terms, all the not equivalent terms, I know that's what I said before, but all the analogous terms, right? So the first term in A is smaller than the first term of B, which is smaller than the first term of C, or equal to it, and so forth and so forth and so forth for each n. Okay, from the starting point on. So n0 is not necessarily one; it's from anywhere of interest, right? Sometimes I need to look at like 10 terms in before I apply this, or before I need to apply this, I should say. And so that's why we're calling this and not just from one, right? Um, if the limit of the smaller sequence is equal in value to the limit of the larger sequence, well, obviously this one in the middle is now squeezed in as well, and it's going to have the same limit as the other two because it is always equal to in value or squeezed between these terms. Okay, so that's a squeeze term. Very, very important. We're going to use this quite a bit for series. It actually drives quite a bit of the work that we do in this chapter. Okay, so the next term, if the absolute value of all of the terms in my sequence, if I look at the absolute value of all the terms in my sequence as n goes to infinity, if that is equal to zero, then the limit of the sequence itself goes to zero. So what does this mean? So let's say I have an alternating series, I'm sorry, an alternating sequence. If I'm looking at just the absolute values of those, and it gets smaller and smaller and smaller, in value to zero, then the limit is also of the sequence itself, the one that actually alternates, that will also go to zero. We kind of drew a graph of that here. So as you can see, yeah, I'm alternating in sign, not in sign, but up and above and below this limit here. Um, let's pretend that this was like positive stuff and negative stuff. So if I was negative, positive, negative, positive, negative, so forth and so forth and so forth, looking at all the negative stuff, they would go to zero. Looking at all the positive stuff, they would go to zero. So if I looked and I made all of these terms positive, the whole thing itself would still go to zero. Okay, so that's what that this theorem is saying, right? If I look at all the positive values of the of my sequence as I get large, if that goes to zero, then my limit, even though it alternates or it can alternate, uh, will go to zero as well. And so just to clarify, I was not saying that this is zero, but let's say that it was. It would be the same graph. Okay, it's the same kind of idea there. So let's do an example. Let's determine if the following sequences converge or diverge. Okay, if they converge, then find the limit. So here, our sequence is the same one that we had at the very beginning, -1 to the nth power, so it's starting negative, n increases by 1. The denominator is being squared and then added to 1. So we'll just go all the way to the beginning because I'm not going to be looking at terms of these. So for this first one, we can see what the terms were: 1/2, 2/5, 3/10, 4/17. So looking at these, my first one is 1/2. This is less than a half. This is a third. This is almost a quarter, right? So it looks like I'm going down in value, right? All the terms in my sequence are getting smaller and smaller and smaller. So gotta go way back. Sorry, guys. All right. So we have a sub n, -1 to n, 1 plus n squared. We have a n for b is the natural log of 1 plus 2 e to the n over n. C is a n is given by n plus 1 to the 1/2 power minus n to the 1/2 power. D is that our sequence is 1 plus n times cosine 2 pi n over n. And E is sine of n plus cosine of n divided by n to the 2/3. So I want you guys to try to do this yourself. Go ahead and pause the video and try to work these on your own. What we're trying to do, okay, so let me give you a little bit of guidance. If the limit of my sequence goes to a value, then it's convergent. Okay, so that's the so let's look at the definition of convergent and divergent here one more time, right? If my sequence, as I get very large, starts to approach a value, I converge. If it doesn't approach a value, meaning infinity or negative infinity, I diverge. Basically, what we're looking at is the limits, right? If the limit of my sequence, as I continue plugging values, approaches a single value, like this did, right? Everything is approaching this value. That's what it means to converge. Now, if it did not approach this value, that would mean that it kind of drifted off in the negatives or drifted off into the positives. That's what it would mean for it to not approach a value. Okay. And so when we're looking at these, that's what we're trying to determine, right? So we have a couple of theorems here, right? I can try to look at similar functions that are less than mine or larger than mine and see if I can use the squeeze theorem. I can try to apply these limit laws by looking at terms individually, possibly, right? So we have a lot of things that we can do here. So, um, okay, first one converges to zero. We already saw that all the terms get smaller and smaller and smaller. And now let's kind of look at this a little bit, okay? I have n over 1 plus n squared. That means that the denominator is always going to be larger than the numerator. Always. Something large on bottom means I'm very small, right? And if I'm getting larger and larger and larger on bottom, I'm getting smaller and smaller and smaller. So if my denominator is increasing in size faster than my numerator decreases in size, really, we're looking at this absolute value wise, okay? Then I am going to converge. Here, I have natural log of 1 plus 2 e to the n divided by n. So my denominator, I know it does go to infinity, it continues to get large, but so does natural log. Okay, so this is going to go 1, 2, 3, 4, 5, 6. Da, 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 da. Does that increase faster than natural log of 1 plus 2 e to the n? I have no idea. But there's limit laws that I get to apply in order to do this. Okay, so I really would want to look at the limit of these things. More so, it's weird finding limits of natural log. I probably want to do something like L'Hopital's rule. Okay, so in this case, it actually does converge to 1. Okay, because if you look at what's really happening here, the n gets large. 1 for large values of n doesn't do anything, right? And 2 will get outclassed very fast by this e to the n. So really what's working is e to the n. And what is natural log of e to the n? That is just n. So when I plug in very large values of n, I basically have n over n, which is just 1. Okay. So we can use L'Hopital's rule, or we can kind of analyze what's happening here. So if I do use L'Hopital's rule, because again, I'm taking limits, right? I can take the limit of the numerator denominator, or I can just look and say, what is my limit doing? Okay, so if the limit goes to infinity, right? If the limit goes to infinity, it diverges. If it goes to a value, then it is convergent. Okay. Maybe you want to pause now and go through the last three since we've gone over two. You're really looking at the limits. Okay, so I'll give you kind of like a 2 count. Maybe you paused it, maybe you didn't. Hopefully you did, and we're back. So now let's look at what happens here. I have n plus 1 infinity minus n infinity, or n to the 1/2. Remember, 1/2 is just a square root. So what happens when I plug in a million, let's say? The square root of a million plus 1 minus the square root of a million. Is that very large? That's a very, very, very small difference, right? And then let's say I go even larger. Let's say I put in a gazillion plus 1 and take the square root and subtract from that the square root of a gazillion. That's even smaller, right? Because the differences are tiny when I have very, very large values here. So it should be very clear that this converges and it converges to 0. Okay. Here, I use L'Hopital's rule. That's why we have the arrow with the H for the first term. But we can also look at it um, and sort of do like a guesstimate and kind of tell what happens by just looking at noticing that I have natural log of e to the n here, and that's what does all the work. Here, using L'Hopital's rule, right, n goes to 1 when you take its derivative. The derivative of natural log 1 plus 2 e to the n is this fraction here, which, the things that do all the work are identical, so it converges to 1, which is the same thing we did here for c. These two things are, in the grand scheme of things, when you plug in very, very large numbers, are the same, right? If I'm playing with billions, adding 1 to a billion is not changing the value much, right? So the difference between those will get smaller and smaller, so it converges to 0. Here, I have 1 plus n cosine 2 pi n over n. If we kind of think what's happening here, uh, 2 pi to the n, well, what is cosine at all terms of 2 pi? So n1 would be 2 pi. N equals 2 would be 4 pi, so another 2 pi. So all of these cosines are the same. Cosine of 2 pi is 1. So this cosine term is always just 1. So I basically have 1 plus n over n. So when you plug in very, very, very large values, right, 1 plus a billion divided by a billion is basically 1, right? That plus 1 extra doesn't really add any information. So this will converge to 1. Okay. Well, I guess we have the answer for this one. For this one, we're going to use the squeeze theorem. Okay. I have sine of n plus cosine of n. If we kind of think about this now, sine oscillates and cosine oscillates. The largest value sine can be is 1. The largest value cosine can be is 1. So the numerator, the largest value can be is 2, and the smallest it can be is 0. Okay. Well, I guess if this is a negative and negative. So 2 and -2 is the biggest thing it could be. Okay. And this denominator just continues to get larger and larger and larger, right? So the problem that we have here is this oscillation in the numerator. But if we're taking something that's oscillating between 2 and -2, and we're multiplying it by something very, very, very small, right? Dividing it by a very large number, its amplitude is going to continue to decrease, right? Which means that this oscillation between 2 and -2 is going to get smaller and smaller and smaller. So it should be very clear that this is going to converge to 0 as well. But we can do this mathematically instead of analytically by using the squeeze theorem, okay? Meaning that I can look at what this is always less than and what it's always larger than, and the limits of those two things will squeeze, right? So the smallest that I can have in the numerator is -2. The largest I can have in the numerator is a +2, right? So this function always oscillates between these two values. The limit of this goes to 0, and the limit of this goes to 0. And so since my function is always between those, it has to go to 0 as well. Okay, so let's look at another theorem. If the limit of a sequence as n goes to infinity is the value L, and the function is continuous at L, function f, then the limit of f of my sequence as n goes to infinity is equal to the function evaluated at the limit of the sequence itself. So what is this saying? If I take every term of my sequence, um, my function is continuous, and I plug in the terms of the sequence into my function, the limit of those values that I'll get out is the same thing as if I just plug the limit into my function in the first place. Okay, so the function evaluated the limit. So let's do an example, not necessarily of this, but we will move on to another example. So consider the sequence r to the n. Okay, if r is equal to 1, then we have the sequence uh, 1, 1, 1, 1, 1, 1, 1 to the n. So again, it's 1 to the n power. R is equal to 1. So if r is equal to 1, the sequence is just all ones, and so obviously it converges to 1. Okay. If r is -1, then it is going to alternate in sign because it's -1 to different powers. So it's going to alternate from negative, positive, negative, positive, negative, positive, but it doesn't ever differ from that, right? It oscillates, it alternates around 0 at a distance of 1, and it never gets any closer. So this has no convergence, it has no limit, and it is a divergent sequence, right? Now, if r is larger than 1, right? Let's say it was 5. I have 5 to the first power, 5 squared, 5 cubed, 5 to the fourth, 5 to the fifth. I just get larger and larger and larger, okay? So it's going to be a sequence that gets larger and larger and larger. So it goes to infinity as you look at its limit. So it's divergent, okay? If I'm less than -1, so it's really the same thing. Let's say I was -5, right? So larger in value, but just more negative, right? So less than -1 means I'm more to the left on the number line than -1 is. So something like -5 would alternate in sign and would grow very large away from 0, right? It would be -5 and then 25, then -125, and then whatever 5 to the fourth is, and then -5 to the fifth. And so I'm large value-wise, it is getting very, very large. So I'm going away from 0 or any value of convergence. So it is a divergent sequence as well, right? It alternates in sign, and it gets larger and larger and larger, so it diverges. Okay. If r is equal to 0, 0 to the n is just 0, 0, 0, 0, 0. So this converges to 0. Okay. And we have one last case, and that is what if r is in between 0 and 1? Actually, we have two cases. So if I'm in between 0 and 1, something like 1/2, 1/3, 1/5, 2/8, 9/10, right? Anything between 0 and 1, 0.00003. When I start putting powers of that, let's just take 1/2 for example. 1/2, so the first power is 1/2. The next one is 1/4. Then 1/8, 1/16, 1/32, 1/64. I'm getting smaller and smaller and smaller. Okay, so if I'm in between 0 and 1, the terms get smaller and smaller, the larger the power gets. And so I diverge because I'm getting closer and closer to 0. Okay. If I'm negative, right, and between -1 and 0, the same thing happens, but I alternate in sign. Okay. So I still converge to 0, but by hopping above and below 0 itself. Okay. So example would be -1/2, +1/4, -1/16, so forth, so forth. So I'm getting closer and closer to 0. I'm just kind of bouncing over the number line over and over again. Now, this is all the cases, okay? And we do this quite often in math. We haven't really had to do that a lot yet in calculus. We did that a little bit when we talked about differential equations and second order equations. We kind of exhausted all the options, but I looked at all the options for r to the n. That's r is 1, r is -1, r is larger than 1, r is smaller than -1, when r is 0, when r is between 0 and 1, and when r is between 0 and -1. So I looked at all of the cases and all the like specialty points, right? 1 being a special point, what happens when it's 1? -1 being a special point, what happens here? Okay. What happens when I'm larger than one of those special points? What happens when I'm less than one of those special points? What happens right in the middle, which happens to be a special point? And what happens when I'm between those special points? Okay, so we looked at all the options, and so if we summarize this, if I am between -1 and 1, 1 being included, I'm convergent, right? Because -1 oscillates, so I can't be at -1, but at +1, it's constant, so it's fine. So any term between -1 and 1, so that's this one, okay, where it converges. This is between 0 and 1, where it converges. This is 0, where it converges. And then this one diverges, diverges, -1 diverges. And the last one right here, the first one we actually was converging. So if I'm between these values, I converge. And if I'm not inside of this interval here, then I diverge for all other values. So the limit as n goes to infinity of the sequence r to the n is 0 if r is in between -1 and 1, is equal to 1 if r is equal to 1, and it's divergent for everything else, right? Which means it would be infinity for any other value. Okay. Or not even infinity because for -1, it oscillates, right? So this doesn't grow forever. It just doesn't converge anywhere. So going to infinity means you're divergent, but being divergent doesn't mean that your terms go to infinity. Okay, because this case oscillates, right? It doesn't converge. It's divergent, but it also doesn't grow uncontrollably. So make sure you're careful with that. Okay. This is very, very important. We're going to use this for the remainder of the course. Okay, so the reason that we went over this and had a whole page dedicated to it is because it is important. So make sure that you remember this. This will help you a ton if you remember these special cases. Okay, let's move on to our next definition. So a sequence A sub n is increasing if A uh, and +1 is always larger than a sub n, right? Meaning that every next term is always larger in value than the previous term. If that's true, then we are increasing. Okay, for every n from 1 for the life of our sequence. Okay, and it's called decreasing if it's the opposite, right? So if as I'm moving forward, my values are always less in value than the previous value, then my sequence is decreasing for every n as well. A sequence is called monotonic if it's either increasing or decreasing, right? So my function's meaning it's always getting larger, right? Every new value is larger than the previous. It's monotonic increasing. If every value is less in value than the previous value, it's monotonic decreasing. Okay. So an example, let's take 1 over 1 plus n. So with just looking at this before we even get into it, does this look monotonic? If it does, is it increasing or decreasing? The main thing that will help you here is understanding this denominator, right? When the denominator gets larger in value, my whole fraction, my whole terms get smaller and smaller. When this value in the denominator is very small, this entire value is very large, right? So when you understand that, it makes this whole chapter a lot easier, right? Just that. So here, what's happening? My n is in the denominator, the numerator stays 1, which means that this is going to continue to get bigger and bigger and bigger in the denominator. And so if the denominator increases, that means that overall my terms decrease in value. Okay, so if I want to look at one term versus how I look at the next term, n plus 1, when I see n, I just add 1 to it. Okay, so it's very, very clear if I want to prove that this is going to be increasing without just saying, oh, look at the denominator. That's where things go up. If I want to look at compare an to an plus 1, okay, when I simplify this, I'm going to have 1 over 2 plus n, which is definitely larger in the denominator than the first term. So that means that this is going to continue to get larger and larger on the bottom, which means smaller in value, right? So my new terms are always less than my initial terms for every value from n from 1 on, okay? Therefore, my function is decreasing. Therefore, it is monotonic, okay? Let's look at another definition. A sequence is bounded above if there's a number m such that my sequence is always less in value or equal to that bound. Okay, so this is very, I was trying not to use the term bounded, but that is what this definition means, right? That the limit of a sequence goes to infinity, that it is divergent. It means that whatever bounds I try to choose, whatever upper bound I try to choose for my sequence terms, there's always going to be somewhere where once I hit that point, the terms of my sequence are always larger in value than that bound I try to find, right? That's what it means for the limit to go to infinity. So it just means I can't find an upper bounds for the terms of my sequence, right? So what is an upper bound? It is just some value m, right, such that the terms of my sequence are never larger than it. It can be equal to it, but they can never be larger than this. So, if the terms of my sequence are never larger than 1, right? It could be equal to 1, but never larger than 1, then my sequence is bounded, okay? I can be bounded above and I can be bounded below, right? For above, we use capital M. For below, we use lowercase m. Bounded below means that my sequence is always larger, the terms of my sequence are always larger in value than that lower bound, okay? It can be equal to that lower bound, but it can't be smaller in value, okay? If I have a function that is, sorry, not a function, if I have a sequence that is bounded above and bounded below and is monotonic, oh, I'm sorry, I'm skipping around a little bit too much. So if it's bounded above and bounded below, then it's a bounded sequence. Bounded sequences are very, very important to us when we get into real analysis for those math majors in this course. Um, we always would like to look at a bounded sequence. It's very, very nice stuff happens when a sequence is bounded. Okay. The monotonic sequence theorem says that if we have a sequence that's bounded and monotonic, then it converges. Okay. So every bounded monotonic sequence is convergent. This is a very, very powerful theorem. Again, in analysis, we use this quite a lot. Okay. So if I'm bounded above, I'm bounded below, and my sequence is increasing or decreasing everywhere, then I am convergent, right? So this should make sense. If I'm bounded below, if my sequence is increasing and I'm bounded below, it's very easy to be bounded below if all the terms are larger in value than the previous. But if I'm increasing and I have an upper bound, that means that it has to approach that upper bound, right? Because if I'm always getting larger in value, but I never get larger than a certain value, it has to approach that value or some value near it, right? So that is the convergence, the monotonic sequence theorem. Very, very important sequence, or a very, very important theorem. Let's do an example. Okay, let's consider the recursive sequence given by a1 is 2 and an being 4 minus 1 over the previous term. Okay, so when we first did this, we used an plus 1. Here we're using just an, but it's the same thing, right? So this is my first term. So my second term, a2, is going to be 4 minus 1 over an minus 1. So that would be 2 minus 1 would be a1, right? So my second term would be 4 minus 1 over 2. Okay, so 4 minus 1 half is what I would have for my second term. So it would be 2, and then what would that be? 3 and a half, right? And then the next term, I can't even tell you what that would be, right? So 2, 7 halves is 3 and a half, and then 26 over 7, I'd have to actually calculate that out. I'm leaving that for you to do as you watch this video. The next one after that would be 97 over 26, and so forth and so forth and so forth. Okay, so these terms are always less than 4 because the way that I find my terms is by taking the previous term and subtracting it from 4, right? Um, so 7 halves is 3 and a half. 26 over 7 is less than 4 because I had to subtract something away from 4, right? 28 over 7 would be 4. Same thing here. 4 would be, what would that be? 4, 108, 98, possibly? I don't know. You can do the math for it, but it's less than 4. Okay. Therefore, it is bounded above, right? It's bounded above by 4. It's also always positive, so it's bounded below because it's never 0 or negative, right? All the terms are positive. So I'm bounded above, I'm bounded below. Okay, I could even probably choose something to make it even closer to. I could probably say it's bounded below by 2, right? Because I'm getting closer and closer to 4 and further away from 2, and I'm allowed to be the lower bound, right? This is 3 and a half. This is almost 4. This is very, very close to being 4, right? 'Cause that's bothering me. That'd be what, 52? This would be 104, right? 104 over 26 would be 4. And so it's very close to being 4, but it's not, right? So each time I'm subtracting a smaller and smaller amount away from 4, which means that this is approaching 4. Um, so it equals 2, but it'll never be less than 2. So I could also bound this below by 2. So bounded above by 4, bounded below by 2, or 0. So my sequence is bounded. Now, if I can figure out whether this thing is always increasing or decreasing, which we kind of already walked through, I could say that it's monotonic, and then I can use the monotonic sequence theorem, which is my goal. Easier way to do this is to just check the terms in general, right? I don't want to do math because what if somewhere down the road something different happens, right? I only have 4 terms. How many terms would I have to check to make sure that it's following the pattern that I think that it's following, right? So what we want to do as mathematicians is use the formula that we're given and not the terms that we're calculating, right? So if I want to look at a n plus 1, I know what n is, a sub n. So what would a sub n plus 1 be, right? It should be 4 minus 1 over a n, right? The next term is 4 minus 1 over the previous term. So for a n, the previous term was a n minus 1. For a n plus 1, the previous term was a sub n. So that's cool, but how does this tell me whether or not right? What I'm trying to do here is try to figure out if an is larger than an plus 1, or is it the opposite? Is an plus 1 always larger than an? Because I need one of these things. I need it to be decreasing, or I need to be decreasing, right? Increasing or decreasing. Okay, it could be neither, to be honest. So I start with my formula. Well, guess what? I know what a sub n is. It's 4 minus 1 over a n minus 1. So I'm going to replace this with its definition, right? So the next term is 4 minus 1 divided by the previous term, which was given to me by 4 minus 1 over a n minus 1. So when I do some math, I would like to have a fraction and a fraction and a fraction, right? So let's kind of try to combine like terms. So my denominator here is an minus 1. So I'll multiply this 4 top and bottom by a to the n minus 1. So I have a common denominator of a n minus 1. My numerator is now 4 an minus 1 minus the one that was there. I still have 1 divided by a fraction. So what am I going to do? I flip the denominator and multiply it. So I will have 4 minus a n minus 1 on top and 4 an minus 1 on the bottom. Same thing, let's make a common denominator. Well, the common denominator is this 4 an minus 1. So I have to multiply that top and bottom. So I will have 16 a n minus 1 minus 4 minus a n minus 1. Or I can just start to use some inequalities because my definition is based on equality. So I could do fancy stuff instead. We do a lot in this chapter. Okay. So instead of trying to see what this is equal to, I know that this is larger than if I were to take away this minus 1. Okay. So 4 minus a n minus 1 over 4 a n minus 1. I could cancel this, but then I'm going to have 4 minus 1/4. And that has nothing to do with a n minus 1 because I'm trying to compare a n plus 1 with a n, right? What I'm trying to get is that the next term is more than the previous term, or that the next term is always less than the previous term. So if I cancel out this, I will have a n plus 1 is always larger than a constant. And that doesn't help if I'm trying to compare this to term by term. So what I'm going to do is I'm going to go ahead and I'm going to separate this. Okay. I know I could write this as an minus 1 over 4 times 1 over this denominator. So instead of canceling out, kind of separate the two fractions, right? And then I can write another inequality, right? Because this 1 over an minus 1 is less than in value than if I had this whole thing, right? I have 4 minus a term in the denominator. So this is basically 1/4, right? If I cancel these out, it's basically 1/4. 4 minus 1/4. That would be less than if I had 4 minus some other value that was not 1/4. Okay, that's less than 1/4 actually, right? So I have this amount times that. So I'm subtracting a larger amount. So this will be larger in value, right? A fraction that's smaller. 4 minus 1 over an minus 1 is the same thing as a sub n. So what I've shown is that my left-hand side is larger than twice a sub n. Okay. So my sequence is always increasing in value, right? So it's monotonic. Okay. It's always increasing. The next value is always larger than the previous. So it's monotonic and it's bounded. It's bounded and monotonic, which means that it converges. Okay. So therefore the limit exists and it goes to L. The limit of my terms is the same thing as if I was looking at all the limit of the previous sequences. which is going to equal L. Okay. Meaning that if I so instead of looking at 2, 7, 2, 2, 6 over 7, 9, 7 over 6 over 26, let's say I just looked at the first three instead of all four. They're going to be going to the same limit that all four of them are going to, right? Because I'm not stopping at 4. I'm really talking about what happens at infinity. So they're basically the same sequence. They converge to the same term, and I can use this fact, right? So as n goes to infinity, n minus 1 also goes to infinity, so they converge to the same limit, right? So if I take the limit of both sides, right, of my sequence, right, uh, here we go. The limit of a to the n is the same as the limit of 4 minus a to n minus 1. So L is 4 minus 1 over L. So basically what I'm doing, I know that the limit of this is some number L, and the limit of the a n minus 1 terms is also L, so I'm just replacing that. This is L, the limit of 4 is 4, minus 1, or minus 1 over the limit of this is also L. So we get L equals 4 minus 1 over L. I'm going to try to solve for L. You multiply L times everything, so I get a L squared equals 4L minus 1. Okay, zero it out. I can't factor, but I can definitely use the quadratic formula. Okay, and I get uh, minus b plus or minus um, b squared minus 4ac over 2a. 16 minus 4 is 12, which we see here. 12 is just 4 times 3, so there will be a 2 on the outside and a 3 on the inside. 4 over 2 is 2. The 2 that was here over the 2 goes away, and I'm left with root 3. So my limit is 2 plus or minus root 3. Root 3 is a little bit more than 1. It's like 1.4 something or 1.7 something. I don't remember. Um, but this is always positive, so we're going to stick with the positive term here. Okay, so it's always positive, so we use the largest value. So this is my limit of my sequence. So I was able to show that it converged, and I was also able to compute its limit without having to look at everything. Especially since from looking at this, you can tell it's getting closer and closer and closer to 4. And so if I had used the 2 minus something term, that would have been very, very close to 1, right? So if this is 2 minus 1.7, it's like 0.3, right? 2 plus root 3, that's almost 4. So it's very clear that this is the limit that applies just by looking at what my terms are starting to go to. Okay. So I hope this was helpful. A lot of information, very, very technical, a lot of definitions. We have limits in here, all kinds of stuff. So if you found this semi-difficult, you can again go to the pre-calculus video and look at that sequence terms. I spend a lot more time looking at actually term by term stuff in that video and looking at the recursive forms and things like that, like the more algebraic portions of it. Obviously, not the um, calculus kind of stuff that this is applies to. Okay, so our next video, 13.2, is going to be all on. It's going to be introductory into the series, and you're already somewhat familiar with series, but we're going to get much deeper into it. And again, you can look at the pre-calculus stuff for that also, in order to refresh your memory or help you to get ready for the stuff that we're going to do, because there's stuff in the pre-calculus stuff that I don't talk about at all, right? And there's some stuff that we do cover, so it's a good uh, review. Okay, see you guys on the next video. Thanks.